Welcome to qnawire.
We have this system here that rotates with an angular velocity in the counterclockwise direction, and we're asked to find what the angular momentum is about the point G, and also find what the angle is between the angular momentum and the axis from A to B. So we're given a weight of the system that's equal to 10 pounds, and we've converted it to mass by doing 10 divided by the acceleration due to gravity, and we'll get a mass that's equal to 0.3105. And these are the equations. So to solve this problem, we're going to have to find the different components of the angular momentum. So we're going to be using these equations here to help solve for that angular momentum. So we'll start the problem by finding what the x component is of the moment of inertia. And from the diagram, we can write this as 4 times 1 over 3 times the mass of an individual rod times the length a squared plus 2 times mr times a squared. And to get this individual mass, mr, so mr, we just take the total mass of the system and divide it by 8, since there's 8 different rods on this system. So the total mass divided by 8, and this will give us 0.03881. And this length A is going to be the length of 10 inches in feet. We're going to convert it to feet. So I of x is going to be equal to 4 times 1 over 3 times mr times the length A, which will convert into feet, squared plus 2 times mr times a squared. So this component is going to be equal to 0.08983. And now for the moment of inertia about the xy direction, this is going to be equal to 0, since if we look at the free body diagram, notice that in the xy plane, we don't have any rods, right? Like it's all in the xz plane. So there's no moment of inertia in this xy plane. So now for the xz plane, that's going to be equal to 2 times the mass of the rod times a squared. So we just plug in. And now this moment of inertia will be equal to 0.0539 pounds second squared per feet. So now we can use these equations here, since we're given the angular velocity as 12 radians per second. So h of g in the x direction, that's going to be equal to 0.08983 times 12, and that's going to be 1.07796 pound-second feet. Now we get our y component, which is going to be 0 times 12, which will just be 0. Now we're going to get our z component. So that's going to be negative 0.0539 times 12. And this will be negative 0.6468 pound-second feet. So we now have the different components. We have the x, y, z component. So we can now write the angular momentum as a vector and then take the magnitude of that vector. So h of g, you can write that as 1.07796I minus 0.6468J. And this should be the k component. This j should be the k component. Right, since we have no y component. And this is the z component. So now we're going to take the magnitude of this vector. So h of g as a magnitude is equal to the square root of 1.07796 squared plus 0.6468 squared, and that's going to be equal to 1.257 pounds second feet. So now to find the angular moment, we just have h of g times the angular velocity. So that's going to be equal to 1.257 times 12, and this will give us an angular moment of 12.93 pounds feet. And now for the angle between h of g and the axis AB, we can say that the cosine of theta is equal to hg dot the angular velocity divided by those magnitudes, multiplied by each other. So we can now write that. We write cosine of theta is equal to 12.931 divided by 1.257 times 12, which is equal to 0.8571. And we now write that theta is equal to the cosine inverse of that value. And this will give us an angle that's equal to 30.99 degrees.